Hi, welcome to Section 3, Walkthrough of an NLP Problem. In this section, you'll walk through a simple NLP-ML problem. You'll apply the tasks from the previous video to this problem. The first step is analyzing the business problem. In the walkthrough, the business wants to quickly identify negative reviews of products. These reviews can then be flagged for a customer service agent to address and possibly respond to the comment if it's appropriate. Today, the business identifies about 30% of negative reviews, but they would like to identify 90% of these reviews. Right now, the problem is solved by a person, an analyst named Nikki. She spends much of her time reading comments and deciding if they need a response. She can only review a subset of the comments in the time she allocates to the task each day. Because her time is limited, many comments remain unidentified. This situation is having a negative impact on the business. Nikki has collected reviews in a spreadsheet, and she's labeled the reviews as either positive or negative. So Nikki's created a labeled data set, and there are two outcomes to be predicted. It sounds like this business problem could be a binary classification problem. When you review the data, you notice that it's organized into 6 columns. The review text column contains the full text of the review. In contrast, the summary column only contains a short summary of the review. The verified column indicates if the customer actually purchased the product. The time column indicates the date and time of the review. The log votes column has the number of votes, which are adjusted to a logarithmic scale. And finally, the is positive column has numeric values. A value of 1 indicates a positive review, and a value of 0 indicates a negative review. You'll notice that the sample data isn't at the text quality of a scientific journal. The text contains excessive punctuation, some words in all capitals, and some codes, such as the /n. Here's the overall distribution of the data. There are 43,692 positive reviews and 26,308 negative reviews. There also appears to be some missing data. Some of the text processing steps you might want to consider are removing stop words, converting text to lowercase, removing extra white space, removing extra spaces and tabs, and finally, removing HTML tags. Note that you might not want to remove all the stop words. Here's why. Consider the following 2 sentences. I didn't love this product. I love this product. The first sentence, I didn't love this product, is a negative comment. The second sentence, or I love this product, is a positive comment. If you removed all the stop words, the first negative comment would be converted to love product, and the second positive comment would also be converted to love product. Clearly, both of the converted phrases express the same intent, love product. However, the original comments expressed opposing sentiments. One was negative and the other one was positive. So when you remove stop words, be sure you take into account the problem that you're trying to solve. Now that the text has been processed, the next step is to put the data into the format that's needed for machine learning. For the text columns, you could use a vectorizer to convert the text into multiple numerical columns. For the numeric data, you might want to fill in any missing values and convert the numerical values into a common scale. Because multiple tasks are performed on the data, a common ML technique is to create a processing pipeline. You can define a processing pipeline in your Python code to make it easier for you to process data. You'll learn how to construct a processing pipeline in the lab for this module. The last processing task is to switch the 0 and the 1 in the is positive column. Why? Recall that the business goal is to correctly identify the negative reviews, which are represented by 0. Metrics produced by algorithms are usually geared towards identifying the positive value. If you want to use the built-in metric, you need to switch the values in the column. After you process the data, the next step is splitting it into multiple sets. These sets are usually training data, validation data, and testing data. Training data includes both features and labels. It feeds into the algorithm that you selected to produce your model. Then you use the model to make predictions over the validation dataset. The validation dataset is where you might notice things you want to tweak, tune, and change. Then when you're ready, you run the test dataset. It includes only features because you want the labels to be predicted. The performance you get with the test dataset is the performance that you can reasonably expect to see in production. When you use the holdout method, a common split is using 80% of the data for training, 10% for validation, and 10% for testing. Or if you have a large amount of data, you can split it into 70% for training, 15% for validation, and 15% for testing. The final step is training the model. The walkthrough uses the linear learner algorithm that's built into Amazon SageMaker. With linear learner, you'll need to set a few hyperparameters. The first hyperparameter is predictor type. The sample problem is a binary classification problem, so the predictor type needs to be set to binary classifier. Next, you'll need to configure the binary classifier model selection criteria. The business case requires identification of the correct or positive classes. So this setting is configured to recall at target precision. This setting is why the 0 values and the 1 values were swapped in the is positive column. The output of training the model is a trained model and a set of metrics. The metric that's most interesting to the business case is validation recall. This metric can then be used when you tune the model with hyperparameters. For example, you could use a hyperparameter tuning job in Amazon SageMaker. You can also use this metric to measure the impact of changing some of the text processing steps. For example, you could change the vectorizer that you use, or you could incorporate other steps. Thanks for watching. In the next video, you'll learn about the different NLP architectures. Hi, and welcome to Section 4, Evolution of NLP Architectures. In this section, you'll learn about the history of NLP and the various architectures that are now used for cloud-based NLP solutions. In this video, you'll learn about 3 NLP architectures: recurrent neural networks, or RNNs, sequence-to-sequence models, or sec-to-sec, and transformers. Before you learn about these architectures, though, it's important for you to understand some NLP history and to understand the relationship between NLP and neural networks. NLP problems have been studied for a long time. As far back as the 15th century, there were philosophers and mathematicians who proposed the creation of a system for translating between languages with code. During and shortly after World War II, mathematicians proposed using some of the encoding techniques developed for military purposes to create automated translation machines. One of the well-known artifacts from this period is the Turing test, which was developed by Alan Turing in 1950. The Turing test determines whether a machine exhibits intelligent behavior that can't be distinguished from human thought. The lack of a linguistic model was a major stumbling block for many of these early approaches to NLP. This situation started to change in the 1950s. Noam Chomsky published Syntactic Structures in 1957, which introduced the concept of a universal grammar. It was a major step forward in the field of linguistics. NLP became recognized as a computer science problem in the 1960s. Several significant conceptual frameworks were developed between the 1960s and the 1980s. Two of the more significant advances were the conceptual dependency model and the Augmented Transition Network, or ATN. The conceptual dependency model was developed by Roger Schenck at Stanford University in 1969. It introduced the idea of deriving meaning from human language independently from the words that are included in the input. Augmented transition networks were developed in a similar time frame and were influenced by Shank's work. ATNs introduced the idea of using recursion to parse sentences. These early frameworks were applied to automated translations, early robots, and applications for specific domains. For example, the Shur-du-Lu system was developed by Terry Winograd at MIT in the late 1960s. It could respond to human language commands to manipulate images of wooden blocks. The 1990s and the first decade of the 21st century saw significant growth in the use of neural networks and the use of artificial intelligence, or AI. Some examples of important early developments include recurrent neural networks, which are also known as RNNs. They can pass learning from one layer of the network to another layer of the network. Other developments include long short-term memory, or LSTM, and gated recurrent units, or GRUs. They're both used to optimize neural networks. And finally, sequence-to-sequence models, or sec-to-sec, were also developed. These early neural networks provided an important foundation for the NLP systems that are now used every day. Initially, it wasn't economically feasible to run neural networks in large-scale production. But the growth of cloud computing changed this situation, especially when it's combined with the ability to scale quickly to very high compute capacity on demand. Cloud computing made it possible to develop the NLP applications that millions of users interact with daily, like Amazon Alexa or Google Translate. New NLP architectures have been developed in the current era. For example, transformers are a new architecture that evolved from sec-to-sec models. Neural networks imitate the way human thinking occurs by creating a collection of interoperating nodes. They are divided into three distinct layers. The first layer is the input layer. It captures the dimensions in the set. The second layer is the hidden layer. It consists of weighted nodes that perform functions specific to the problem domain. And finally, the third layer is the output layer. It provides the results of the processing. Neural networks are applied to a variety of AI problems. You can use a neural network for many types of NLP problems, such as speech recognition or machine translation. You need to run neural networks multiple times before you can find the correct number of nodes and the correct weights for the functions in the hidden layer. During the tuning process, you'll find that some weights outperform others. If you track the improvements in output as you change the weights, you'll have a series of number pairs that match the change in weights to the improvement of the function. If you plotted these changes, you'd produce a line. The gradient would be the slope of the line. A gradient that's close to zero means that your model isn't improving. Networks with higher gradients learn faster. Here's an analogy for the gradient. Imagine that you're climbing up a mountain. Each of your early steps up the mountain would take you closer to your destination than the latter steps because the mountain has a steeper slope towards the top. If you measure the distance between the start and end of each step, you'd have a series, just like the series for the change in weights for the neural network function. Although neural networks mimic human thought, they have some limits. For example, humans don't need to evaluate each input from scratch. You can process an input because you already have a certain amount of knowledge. As you read text or listen to a lecture, your mind can process the input from previous cycles. If you think of this series of inputs to your mind as a long-running sequence, then you have the idea of a feed-forward network. As new inputs arrive, the feed-forward network passes the output to the next series of nodes. The problem with a feed-forward network is that the individual network nodes need a way to use the information that earlier nodes already learned. This is why RNNs were developed. RNNs can use LSTM to remember the information that was previously learned. Here's an example of why you'd need LSTM. Imagine that you're creating a typing application that can automatically complete words. You're also using a simple neural network. When you start entering the word government and you get to the letter V, the application should suggest the rest of the word, which is earnment. Without LSTM, the network can't suggest the rest of the word because it will have forgotten about the letters G, and O that came before the V. In the 1990s, researchers who worked with neural networks discovered some problems with managing gradients. For example, accumulating gradients between multiple cycles sometimes resulted in very large updates to the weights that were in the hidden layer. This situation is known as an exploding gradient, and it can lead to an unstable network. GRUs were developed to deal with these problems. Sec-to-sec models were first introduced by Google in 2014. They were designed to address the problem of how to map inputs to outputs, where the inputs and the output sequences are different lengths. For example, say you want to translate the question, "How are you?" from English to Spanish. The English input is 3 words, but the Spanish output is only 2 words, or "¿Cómo estás?" Sec-to-sec models work well for translations because you need to transform the sequence of words from one language into a sequence of different words in another language. LSTM-based modules are generally used for sec-to-sec models because they can give meaning to the sequence, while remembering the parts that are important. A sec-to-sec model consists of a few parts. First, it has an encoder, which captures the input to the model. The encoder is made up of either LSTM or GRU cells. Next, it has an encoder state, which is also known as an encoder vector. This calculates the value for the nodes in the hidden layer. Finally, it has a decoder, which predicts the output based on the input. Sec-to-sec models are used by many systems that respond to human speech, such as Amazon Alexa. The transformer architecture for NLP provides a way to create a sec-to-sec model without using an RNN. It introduces the idea of attention. This concept is another way that neural networks have been adapted to behave more like human thought. When you read or hear a sentence, your brain can evaluate each word in the sequence. Your brain knows that word order is important, so it can immediately infer the meaning of the word in relation to the previous words. So the neural network designer's task is figuring out how to give the neural network this knowledge. The transformer architecture is similar to the sec-to-sec model. However, it replaces the ability of the RNN to retain knowledge between iterations with a layer that retains the position of every word in a sequence. The bidirectional encoder from transformers, or BERT, is a model that builds on the idea of transformers to fine-tune pre-trained NLP models. It's been used to improve the performance of various NLP tasks. Thanks for completing this module. In the next module, you'll learn about how to process text for an NLP application. See you in the next video.
Hi, and welcome to Module 3, Processing Text for NLP. Here's what you'll learn about in this module. In the first section, you'll learn about the major steps you'll take when processing text for your natural language processing application. The next section describes how to extract text from various sources. The third section walks through some of the most common ways to process text. The next section describes how to accomplish the important task of converting text to numbers. Section 5 explores some more advanced forms of text processing. And finally, Section 6 describes the differences between structured and unstructured data and reviews 3 different AWS services you can use to store data for your NLP application. Okay, it's time to get started. At the end of this module, you should be able to define the processing steps for text, implement text extraction to obtain data from web pages, identify tokenizers for text processing, describe the techniques and tasks used in processing tasks, list the advanced processing steps for NLP, and finally, identify the storage services for text in AWS. This section provides an overview of text processing. As you saw in the previous module, the first stage of your NLP application is loading and processing text. You can think of this stage as consisting of 3 substeps. First, you'll need to extract data from the data sources. For example, you can pull text from websites or other web resources. This is known as web scraping. If you're loading data from documents, you'll need to convert it into the form that's required by your loading component. For most real-world applications, you'll want to automate the extraction process. After you've extracted the text, you load it into the transform pipeline. In this module, you'll learn how to do this with Python libraries, but you can also automate it with Amazon Textract. Finally, you'll need to transform the text into numeric representation for use by your machine learning model. You can extract either individual words, sentences, or entire documents of text. You can also extract text data from images. For example, a media company might want to find all images containing the name of a particular brand or product. Another common use case is extracting data from forms or other types of structured data. For an example, a human resources department might want to find all employee records containing a particular set of skills or experiences. Amazon has several different services you can use to automate your extract, transform, and load processes, which is also known as the ETL process. You can use AWS Glue to discover the structure of a dataset and to automate ETL processes. The diagram here illustrates the major components for an ETL system based on AWS Glue. First, you define a crawler, which discovers metadata based on your data. AWS Glue then stores this metadata in a data catalog. Next, you can use the script AWS Glue creates for automating the ETL process. You can also create your own script. When you have your data transformation script, you can either run it on demand or create a schedule for running it. The script extracts data from your data source, transforms it, and loads it into the data target. You can use AWS Glue for a variety of ETL jobs. Here are some common examples, but there are many more. Some companies have built DevOps pipelines to automate troubleshooting and analyzing customer logs for a web hosting service. Another use case is to automate extracting information from a data lake to inform analytics for online retail. You can extract data from earlier data stores to forecast future sales with AWS Glue. And finally, customers have discovered security threats by analyzing data breaches and web traffic. Thanks for watching. In the next video, you'll learn about AWS Glue and Amazon Data Wrangler. Welcome back. In this video, you'll continue learning about Amazon services you can use for text extraction. AWS Glue Data Brew is a fully managed AWS service you can use to visually prepare, clean, and normalize data without writing any code. AWS Glue Data Brew includes these key features. You can explore data in columns with rich statistics using visualizations to find anomalies and patterns in the data for each column. You can also clean and normalize data using over 250 built-in transformations. These include removing or replacing null values, standardizing date-time columns, creating encodings, and creating aggregates. You can also merge, pivot, split, or join data. You'll need to work with representative samples of the data to determine the right transformations you need. You can build and experiment with recipes using one or more transformation steps. Each transformation is added as a step to build recipes. You can save, publish, and version recipes to share with other collaborators. Finally, you can run jobs to apply the recipe on all incoming data or run a job to apply the recipe to larger dataset. You can specify data formats, compression modes, and partition keys as you output prepared data to Amazon Simple Storage Service or Amazon S3. When you import data into AWS Glue Data Brew, you can view key information about your dataset, including missing cells and duplicate rows. Data Brew also gives you a quick data correlation chart so you can see key relationships between features. Going into the columns, you can view all the common statistics on column data. For text data, this includes top unique values and value distribution data. With the data imported, you can then create a project. You use a project to define a set of recipes, which are actions you can perform on the data. DataBrew also gives you some recommendations based on the column's data type. For processing text, you can select some of the common processing tasks you'll learn about in this module, like formatting, cleaning, extracting, handling missing values, word tokenization, and categorical mapping. AWS Glue DataBrew can also tokenize text, remove stop words, expand contractions, and perform stemming. You'll learn more about all of these later in Section 3. These tasks are all done without code and can speed up data processing for an NLP project. The data processing steps are compiled into a recipe. The example recipe changes the text in the review text column to lowercase, removes any special characters and white space from the review text column, and tokenizes the review text column. You can create a recipe job from a recipe. A recipe job can be run manually or on a schedule you choose. DataBrew maintains a view of the data lineage. The data lineage includes information about the origin of the data, what happens to it, and where it moves to over time. This can be useful for troubleshooting issues. Amazon SageMaker Data Wrangler is another approach you can take for capturing text for your NLP application. With Data Wrangler, you can do the following. First, you can import data from Amazon S3, Amazon Athena, or Amazon Redshift. Next, you can create a data flow to complete data preparation steps. You can use one of several built-in transformers to perform operations such as string manipulation or vectorizing your text dataset. In addition, you can build visualizations of your data such as scatter plots and histograms. And finally, you can export your data into other SageMaker services using a Data Wrangler job or a SageMaker pipeline. You can think of getting text into the ML pipeline as being the extract part of the ETL process. You learned about two general patterns for getting text: web scraping and extracting from data stores. You also learned about AWS Glue and the Amazon SageMaker Data Wrangler for extracting data. Thanks for watching. In the next video, you'll learn more details about extracting text. Hi, and welcome to Section 2, Getting Text. In this section, you'll learn about some of the more common ways of getting text. Extracting text from the web is a common way of getting text into your NLP pipeline. Beautiful Soup and Scrappy are two of the more widely used tools for doing this. In the lab, you'll use Beautiful Soup, but both tools follow the same general process. In this example, you might want to extract some key information from a web page, such as stock pricing. The information you need is located among other data. Using text extracting tools and some basic HTML knowledge, you can write a script that extracts the information you need and stores it in a format that's more useful for solving your business problem. Amazon TextRact pulls data directly from scanned documents. You can either interact with Amazon TextRact by importing scanned images in the AWS Management Console. You can also use the AWS CLI or the API to automate the import process. Amazon TextRact organizes text as individual blocks it detects in a document. Documents are made up of pages. Pages can be of different types, such as individual lines of text, tables or text, or key value pairs. After you extract the text, you'll load it into a processing pipeline. In the lab for this module, you'll load data into a data frame using Pandas, which is a Python library. You can also use the Amazon TextRact service. With Amazon TextRact, you can automate the loading process through the AWS CLI or by calling the API directly. The screenshots here show Amazon TextRact Analyze Document page in the AWS Management Console. This example is loading text from an employee application form. You can also view text as raw text or as a table. In this section, you learned how to capture text for your ML pipeline. You can either use Python libraries like Beautiful Soup, or you can use a service like Amazon TextRact. You also learned how Amazon TextRact pulls text directly from scanned documents. It can extract raw text and tabular data. It can also extract information from form controls like checkboxes or option buttons.